The lab this week was about projectile motion. The general idea of this lab was to record an object being thrown to represent 2D projectile motion. From that, we created a model inside of GlowScript to simulate the same object in the same motion, and then created different models to better visualize the different methods of data points taken. In this lab, we used a few different known values and equations to compute a model. The first value is that the net force of an object in projectile motion is just the force of gravity, so F net just equals negative mass times gravity. Then the equation that we used were the velocity and position update formulas, which is the final velocity equals the initial velocity plus the net force divided by the mass times the change in time. And then the final position equals the initial position plus the initial velocity times the change in time plus the net force divided by the mass times the change in time squared. For the object and projectile motion, we created 3 separate sets of data from the one object. The first was the data points from using tracker, the second was a computational model without drag, and the third was a computational model with drag. For the force of drag acting on the object, we use the equation F drag equals negative v times v squared times v hat. In this case, v is the drag constant, v is the magnitude of the velocity, and then v is the unit vector of the velocity indicating direction. For the tracker model, I went frame by frame from the time the object was released to the time it hit the ground, taking data points at each time. From there, we created a graph of the x position of the object versus the y position of the object. And then here we have the x and y position with the graph representing it. For the first computational model, it was just a model with gravity affecting it. For the computational model with only gravity as fnet, we used GlowScript to create a program that would create a model. Well, we had fnet include the force of gravity and the force of drag. Since the drag constant is set equal to 0, the net force is equals the force of gravity. And then here's the code we used to include it, and then some more data points with the graph. The next model we used was a model that had both drag and gravity. For the computational model with both gravity and drag as the net force, we used GlowScript again to create a program that would create an accurate model. We made sure that the net force included both forces so that when the drag constant wasn't set equal to 0, the equation for the net force would now account for the drag force. And then here it's the same equation used before, but since b isn't set equal to 0, there is now an actual value for the drag force. And then it's another set of similar data points in the graph. Once we had all of the data sets we needed, we plugged in all of those points into one graph to better compare the sets of data. While the points are close, there's a difference between the 3 sets. The observational model was the base set that we used to compare the other models to, and was the one that went the furthest. The predicted models were both closer together than with the observed data, and then with the drag model, no drag model going slightly further than the with drag model. In the context of this experiment, we threw the object at an angle. This meant that it had constant horizontal velocities greater than 0, and constant vertical acceleration from the force of gravity. If we had thrown the object straight up from the same point at the same speed, it should take the same amount of time to reach the ground. The only thing that would be different is the change in the x position. Since we threw it straight up, it wouldn't change in that direction, but the vertical acceleration would be the same. And then for any computational models predicting terminal velocity, the only one that might get close to predicting that is the model with drag, since that would be the only force countering the force of gravity. In the model with just gravity, the net force is greater than 0, since gravity is acting downward with nothing acting upward on the object. One experiment that I think might predict this value better would maybe be dropping an object with a small parachute of some sort. The parachute would add air resistance upward to counter gravity, so you would only need to just do some simple calculations to make sure the value of the forces are equal and opposite to each other.